Okay. My name is Joseph Warren. I'm a principal software engineer at Microsoft, and one of my most recent projects was doing the MAPIHTTP protocol for Exchange and Outlook. Sorry if I seem a little sleepy. I have a newborn at home, so I don't get a lot of sleep anymore. It used to be I was up late coding. Now I'm just up late doing other things. So if I nod off, just scream at me or something. So MAPIHTTP. What is MAPIHTTP? It's basically a lot of these slides. I don't know if some of you were here last year. There's probably some duplicates of some of the slides, but I thought I would go over some things initially just to, if you hadn't seen it before. But MAPIHTTP is a replacement for the RPC over HTTP protocol between Outlook and Exchange. It conforms to HTTP 1.1 specification. It's exclusively based on HTTPS. There might be some groans in the room, but that's the way it's currently implemented. And it uses the post verb for everything. It gives us the ability to push data up and get data down. And it's connectionless, but it is not stateless. And I'll explain more what that means in a few slides. The goal of MAPIHTTP was to overall reduce the complexity of how the client connected with Exchange. Traditionally, it was just using TCP, RPC over TCP, and it was a very direct communication. But we found problems with that when we wanted to start doing the Outlook Anywhere. We had to be able to tunnel in through firewalls, and doing direct TCP was not a good approach. So we leveraged some work that was being done by the Windows team for RPC over HTTP. But it had its own set of complexities. There was, it had dual channels. You had to authenticate on the HTTP connection, and then there was an inner auth. You had to have multiple HTTP channels, one for inbound data, one for outbound data. There was a lot of complexities there. So MAPI over HTTP, we wanted to try to reduce that complexity. So the communication between the client and the server was more in line with some of the other protocol offerings within Exchange, like EWS and OA. Everything is just very HTTP, single request response oriented. So this allowed us to no longer have the inner and outer channels of the RPC pipe. There was no dual channels. There's no paired in and out connections. We got rid of the infinitely long request and the infinitely long response that RPC over HTTP was designed around. And also, we eliminated the tying of the actual session that the client had with the server on a very specific TCP connection. Or I guess in the case of RPC over HTTP, it would be a pair of HTTP requests. If any one of those requests was terminated, the session was run down on the server, and the client would have to go through the process of reconnecting. So in a world where the network could be a little bit flaky, your client would be disconnecting and reconnecting quite frequently. So this allowed us to do some clean transitions between networks. So now we aren't specifically tied to a connection. The client could essentially hibernate, or if your network changed, if the client detects it's going from a wired connection to a wireless connection or vice versa, it could pause the connection and then resume it on a different protocol adapter.
Joe,
yes?
when you say session, do you mean the connect or the logging?
Right. I mean,
which one of the session context?
On the session context, the connect. In the RPC world, the way you would connect is you would call this ECDO connect EX function, yes. And you basically, to the server, you say, hey, I'm user A, I want to authenticate, and it would authenticate you, and it would create a context on the server or a session on the server, and it would return this context in the form of an RPC context handle to the client. And then subsequently, if the client wanted to issue other requests up to the server, there was another method. If we're talking EMSMTP, there's another method to pass up ROPs, and so on and so forth, to do operations on that context. MAPI over HTTP is very, very similar in that there is a request well, maybe I'm getting ahead of myself. It's in later slides. But you essentially, you establish, you do a connect request. It generates the same session, but it doesn't return it as a RPC context handle. It returns it as a cookie on the request. So the client stores those cookies, and whenever it wants to do another operation on that session context, just replays those cookies in subsequent operations. So yeah, back here, so we were also able to solve the issue where a laptop, if it was to hibernate and come out of hibernation for a certain period of time, the client didn't need to actually go in and reconnect and re-log on and reestablish everything. The session should still exist on the server. And short term right now is 15 minutes. So if you're to hibernate from, say, here and go down the hall and open up your laptop again, it wouldn't necessarily need to reconnect. It also allowed us to support new authentication types. The RPC over HTTP, since it was designed by the Windows team, and there was a lot of code there that it was difficult and hard to kind of change. It's one of those, you know, it's not owned by Office. It's hard for Office to iterate on it and make changes to it. And we're growing faster than RPC over HTTP is because they're not doing a whole lot of investment anymore. So it was hard for us to get in and do other kind of things with the protocol between Outlook and Exchange. So we wanted something that we could potentially do other authentication types more easily. Also, the protocol. Question?
Yeah, so the short term is basically means that 15 minutes the Exchange will put in the session.
Yeah, in 15 minutes, if it doesn't actually hear from the client, a request is made, it will just run it down, kind of like in the old RPC world, if connection was lost, the server would get a rundown and it would clear everything up. Which is fine, because the client would then, when it comes out of hibernation after 15 minutes, he will just issue a request, and the server will say, oh, I don't understand that cookie anymore, and the client knows I need to go through the process of doing the connect and the log on, and like it did traditionally. Also, we defined clear expectations for timeouts. In the RPC over HTTP, there was some hard-coded, some embedded timeouts within the protocol that we didn't really control because the RPC layer on the client was speaking to the RPC proxy layer on the server that was owned by the Windows team, and there was a lot of weird timeouts involved with, you know, if one channel made it to the server but the other channel didn't. Sometimes you would be sitting there trying to connect for 30 minutes, an hour, and it was kind of a bad experience. So this protocol allows us to clearly define the expectations that the client should never really ever be in a situation where it doesn't know what's going on. It should never be waiting indefinitely for something. So the client knows within a very short period of time, I believe 40 seconds, 60 seconds, that it knows that there's something wrong and it needs to disconnect and try again. Okay, so previously this is kind of what the connectivity with RPC over HTTP looked like. There was dual channels. There was an infinite request that was pushing data up to the server, and there was an infinite response request that was streaming response data down. So there was kind of this paired HTTP requests, and that kind of was logically the connection with the server. And then the RPC proxy, which is a separate piece outside of Exchange, had to run on the server, and it would actually speak to the actual Exchange backend server. This is an interesting map. This is actually a Exchange 15 view of the world. It looks slightly different in Exchange 14. I was going to do another slide to compare, but I kind of ran out of time. But this is what it looks like in 15, where the requests kind of go through to the back end. On 14, the RPC proxy actually existed on the CAS server, and then it had some complex logic of sewing the connections together to go to the back end. The new world with MAPI over HTTP, it's just single request response. We go through the front end, it goes to the back end, and the ROP data is actually, well, maybe ROP is a bad term there. I mean, whether it's a connect request or a request that has ROPs or an NSPI request, it's all just payload data that gets passed up as a request and then a response. Okay. So how does a server know if a client supports MAPI HTTP? And we solved this problem by just extending autodiscover. So the client passes up an autodiscover request, something like this, and we added a new header that the client passes to the server. It just says, I support MAPIHTTP. There's a number after it, and that's an actual version, meaning I support the first version of MAPIHTTP. It's kind of a protocol versioning thing. The server can look at that, and an older server would just ignore this header, and you're going to get the autodiscover that you would normally have gotten, in which would have included Outlook Anywhere settings for RPC over HTTP, and the client's happy with that and continues on. But if the server understands this header, he would essentially, this is how he knows that the client, or the client knows that the server supports it, he would actually return something very, very different to the client, is that his actual autodiscover response includes a new protocol type called MAPIHTTP, and the version here is the highest, the client, yes, the lowest common denominator between the client's reported version and the server's reported version. And if there is no lowest common, the server can default to returning RPC over HTTP or Outlook Anywhere settings. So in this case, since there's really only one version of the protocol today, the client says, oh, or the server says, the client is asking for protocol version 1. I support that. I'm going to give him protocol version 1. Even if the server supported protocol versions 2 or 3, he's never going to give the client something different than he knows how to understand. So he returns and says, I support version 1. And this is how you connect to me. There's essentially 2 URLs that are returned. One is for accessing the mailboxes. One is for accessing the address book for the NSPI functionality.
Joe, just a question on
Sure.
what that means. Does that mean if there ever is a version 2, the client will always have to support both versions?
No, the server might have to support multiple versions because we're going to have clients that support, say, version 1. If the server supports version 2, but I see what you're saying. If the client wants to be able to communicate with a version 2 server, but the server comes back and says, I only support version 1, yes, it would have to be able to downgrade. Or it could just say, I can't connect to that. So in this example here, the server is actually configured just to return one URL, but the server, I believe, through some PowerShell command lists, you can actually configure it to return up to 2 URLs for each, an internal URL and an external URL. So depending on how your topology is configured, if the client will always attempt the internal URL first, and if it can't connect, it will then fall back and use the external URL. So if you had a different sort of networking rules inside of your corporation versus outside, the client would be able to connect to it.
So my question is whether if this is like the first choice protocol for the upcoming release, like will it always first try with MAPIHTTP version 1 and then if it fails it defaults to RPC or HTTP? Or is it configurable in the client that you always want to talk RPC or HTTP?
Okay, the question is, see if I get this right. If the client's asking for a particular MAPIHTTP and it can't connect, will it fall back to RPC over HTTP?
No, I mean,
can you configure in Outlook what to do? Or it's coming with something that
by default, the client will advertise that it supports MAPIHTTP. It doesn't necessarily mean the server will. If the server's configured for it, currently in, I believe, SP1 of Exchange 2013, it's disabled by default, and you can enable it. So once you enable it, the autodiscover will start responding to the client's request. The autodiscover payload, when it responds, gives just MAPIHTTP or just RPC over HTTP. It never really tells the client to do both. Now, a client can do both in a sense where if one mailbox is on a server that supports MAPIHTTP, it'll tell it to use MAPIHTTP. But if another mailbox in the profile is on a server that doesn't, it'll tell it to do RPC over HTTP, or public folder, or archive. So it's really based on the server the mailbox is currently on, whether it supports it. Now, you could run into some weird scenarios where it's on a mailbox that or a mailbox server that supports it. The mailbox database fails over to another server that doesn't support it. The client will get some pop-ups. I think we reduced the pop-ups where if the client is perfectly happy communicating and everything, it won't actually pop up telling you you need to restart. Because unfortunately, the client requires a restart when it switches between protocol types. And it detects that in the auto-discover response. So here in my example, I just have one set of URLs. Now the URL is essentially supposed to be opaque to the client. It should take it as is. It really shouldn't try to interpret it. But it's plain and simple, clear as day, is probably you can figure out what it's trying to do here. But the client needs to parse it to a certain point because when it gets down to it, it has to make the request. So it has to interpret the URL. It has to get the FQDN out. It has to get ports out. It has to get whether it's doing HTTP or HTTPS, but it's always HTTPS. But the actual the query string is somewhat opaque. The VDIR path and the query string, because we want the ability and leverage in the future to change that, and hopefully that won't break anything. So how do you establish a session? So this is kind of what a MAPIHTTP request looks like. I will simply walk through here. It's a post. From the auto-discover, you have the VDIR path and the query string that gets sent up. I think last year this used to be just application octet stream, and you couldn't really differentiate, so we decided to standardize on MAPIHTTP. It says that the content of this request is a MAPIHTTP payload. This client info is something that the client passes up. It's not required by the server, but we do use it. We log it. So if the client wants to be able to pass something up where we could track down specific client instances, he could put something in here. There's no real requirement. This has to be a GUID. Outlook does this. It adds a GUID, and the number on the end is if the client has multiple session contexts with the server, it'll just increment the value. Every request has a unique request ID. This is required. The server does check to make sure that it exists. And I do believe the format has to be a GUID and a value. For uniqueness, the client starts at 1 on the connect, and it just keeps incrementing the value with every request that comes up. So that allows us to log this on the server. So if we ever have a problem, we need to actually find a request. If we know what the actual GUID is from the client, we can see all of the requests from that client for that session. The request type is connect. This is how you create a session for the EMSMDB for the mailbox interface. If you want to do the address book or NSPI, the request type is bind. There's a lot of historical reasons because of this. If you know the RPC protocol, it was ECDO connect, so we used the word connect for EMSMDB. And in NSPI, it was NSPI bind was the function to generate the session context on the server. And then the request data. I don't actually go into detail of what the request data here is, but it's just essentially all the parameters that was on the ECDO connect. It's just serialized. It's in the OXCMAPIHTTP document on what these request formats actually look like.
Question?
Mm-hmm.
Go ahead. Request ID, does it have to be globally unique forever, or does it only need to be unique on the session?
Considering that we actually use it for logging, it's probably good that it's globally unique forever. I believe the Outlook client just creates a new GUID and then for the session, and then ticks up. If it generates a new session, it creates a new GUID and starts over at 1. Generally, you'll always see the number is 1 for the connect or the bind, and then subsequently counts up from there. If somebody gets crafty, they could decode my basic authorization header if you feel like it. There's a hidden message in there.
So regarding the increasing of the numbers, is there a requirement? Like because in BCRPC there used to be a requirement that the call IDs has to be monotonically increased or something like that?
I don't think we actually adhere to it. The server doesn't actually validate that.
For the client, maybe.
It's mainly for the client. It's more for debuggability, logging purposes. You know, you get what you give, really. I mean, you could probably just keep giving the same value, but I don't know if it would be very useful. So, yes?
Is there a reason why the request type is encoded as an HTTP header field instead of being part of the URL? Because I would expect such a command to be part of the URL.
You know, we kind of went back and forth. Originally, it was going to actually be part of the body because we didn't, the protocol, we wanted it to be completely opaque. Yeah, I mean, this is a protocol. It has nothing to do with what actually is in the reaction request and response. But then we decided, well, it's really hard for us to log this, especially in the middle tier, the front end, when requests are going through. We can't be parsing the body to be looking for the request type if we want to be logging things. So we decided to actually extract it out of the body and put it as a request type. But yes, it could be part of the URL. But we decided, well, we don't want the client playing with the URL. So here, because it's something that gets from auto-discovery, we want to be able to change it. Now, granted, they could add a parameter on the end, but we decided we didn't really want to get, we want the client to just never really play with the URL. So it just gets the URL, it's fixed, it doesn't understand it, it really shouldn't try to interpret it or add things, you shouldn't try to generate one, you should always just get it from auto-discover. So we opted not to put it into the URL, for good or bad. Yeah, it would have made things easier for just normal logging because there's a lot of tools and products that just kind of log the URL string or the query string, and it would have just naturally been there. Not to say we couldn't add it, but it would probably always stay as a header. So the response looks very much like this. Normally, you always get a 200 OK unless you're being challenged for authentication. I don't really get into authentication here, but I'm assuming everyone understands HTTP common authentication paradigms and how all that works. So the 200 OK generally means the server accepted it. The response code initially means that from a protocol level, the server was able to get the request, parsed it, and everything was good. There was nothing wrong. It doesn't necessarily mean the request is going to succeed. It just means from a protocol standpoint, the server liked the request. Generally, but not always, the server returns transfer encoding chunked, meaning it initially starts sending the response, and then once the request is actually processed and completed, it will then send the rest of it. And there's kind of a way we play some games with meta tags in the response to tell the client, I'm processing it, it's still processing, and then it's done, and it gives the final results. And I have another slide that shows that.
Why did you have to do that?
Well, it was the whole thing where, like in the RPC world, you sent a request, and it goes up to the server. And you wait, and you wait, and you have no idea whether the server got the request.
You can wait for days even.
Yes. So here, this was an idea that the server, as I explained in one of the earlier slides, that there was very specific timings. When you send a request, the server has a very narrow scope of time to actually respond to it, so the client knows, hey, the server got my request. Everything's OK. So if the client doesn't see a response in 30 seconds, it says, something's wrong. In the RPC world, you issue the request, and an hour later, it still hasn't completed, and you don't know why. So here we use chunked so we can immediately respond to it. It doesn't necessarily mean it's actually been processed on the server when you get the initial response, but that it's being processed. Here's just kind of, it sends back the same content type. It kind of beacons back these other parameters. The client info, it just kind of gives back, and the request type it gives back, and the request type it gives back. It's just what was passed up. So here's where, on the connect, we generate cookies and we return them. Now, the cookies themselves are also opaque. The names of the cookies might change. The values, what they mean, might change. So the cookies itself, the reason it's opaque is that the server, the implementation of the server, it could put whatever it wants in there for a cookie. And I'm assuming another server product who is following this protocol, their cookies don't have to map to the values that we use here. They have the freedom to set whatever cookies they want and whatever data they want in them and return them to the client. The client knows that for this session, I have to save every cookie that's returned. This example here only shows 2 cookies. I think in reality, there's more than that because there's some routing stuff through our front end adds some cookies. But the client knows to just record all the cookies and then play those cookies up. Now the expiration info, that tells the client how long the session is good for, how long it is going to be until the server will actually expire it. Now I don't know why we put this in milliseconds. It's a very large number. It's milliseconds. You know, on the order of 15 minutes, maybe we could have just used seconds or even minutes as the units here, but it's milliseconds, so it's 900,000 milliseconds.
It's good for testing if you just want to test the server. You can test like 5 milliseconds.
And we do actually, in our testing, we do that. We pass up, or the server returns different things so we can simulate things expiring faster. So yeah, there was a reason we did this. No, there was no reason. Pending period. This explains the pending period set to 15,000, which is essentially 15 seconds. It means that we initially respond to it because we're doing chunked. We initially respond to the request and we say processing. And the client should expect to see a pending or a meta tag. You should expect to see something every 15 seconds on this connection until the request is done. So the server will, if it's taking a really long time, will keep beaconing these pending, pending, pending to the client. It's kind of like a ping or a keep alive to tell the client, hey, I'm still here, I'm still processing, everything's good. Don't resend the request. OK, and then the response body with the meta tags that I just explained, and I will explain the meta tags, I believe, in this next slide. So the response is typically always chunked, but if the server can process the request really fast, it might opt to not return a chunked response, because I think there's some performance wins by not chunking all the time. If you just have the body, you can just stream it right out. And it doesn't have to put all the chunking markers around the data. So the protocol, basically, since chunking is part of HTTP 1.1, but also not chunking is also part of HTTP 1.1, the server's free to do what it wants. So the response looks like this, and then we kind of went through this. So initially, you'll get this immediate processing marker. Now, I've put the carriage return line feeds in here to kind of get you an idea that there actually is carriage return line feeds. The green stuff that you see there is the actual chunking markers. So you'll initially get this processing response. So the client knows, OK, the server's received my request. I didn't get a response code, a failure, so it liked my request, and now it's processing it. Then every 15 seconds, you'll get this pending and a pending. And eventually, you'll get a marker that says done. And then there's a final response code, because it kind of gives the server the ability. Initially, when I received the request, everything looked good. But when I actually got to the point where I actually was processing it, it didn't look good. And I want to tell the client about it. There's very rarely a case that it would fail at this point. But we added the ability to tell the client later, when it's done, that, hey, there was actually something wrong with it. Then the actual response data. Now, there's some other headers that it actually returns here that I didn't include in the slide because it was for lack of room. Following the response code, there's I think it returns the elapsed time of how long the request took on the server. And I believe it returns the time at which the request was received by the server. But I think that might be able to be inferred by the date header. I don't know if it differs much.
So we'll see 2 X response codes, one in the header and one in the body kind of a thing? Because the previous slide, you didn't have 2 response codes.
Previous slide, let's go back. This one here? Well, all the processing pending is kind of the meta tags in here.
Like
so, yeah.
Response body.
There may be a failure later on once the done tag comes through, and you have to kind of inspect. What we call it is the additional headers. It's headers that really aren't, they look like HTTP headers, but they're really not. It's part of the body. So.
I have a question about the cookie. The cookie, we can see that there is a mapping context. So I'm assuming that ties to the EMSMDB context.
Yeah, while the cookies are opaque, I can explain them. The mapping context is essentially, if you decode it, it's just kind of a mapping to the session on the server. We have what was called a sequence. I have some slides that talk about the sequence. The sequence is essentially a way to prevent the client from just hammering the server with a bunch of requests with that cookie. Because essentially, if it's just a cookie, the client can issue 100 requests in parallel, and the server would get overwhelmed. So what the server requires is that when it processes a request, it returns a sequence in the response to that request. And it's a unique value. So the next request has to have the sequence from the previous request. So it's kind of a daisy chain. And then when it processes, it'll get another unique sequence. So in the response to every request, the client, by the protocol, has to store and update all the cookies that are returned on every request. So it's essentially the first request, you get sequence 0, and it's got some random stuff there. And then in the response to the next request, it'll get sequence 1, then sequence 2, then sequence 3.
So if you want to do things in parallel, you have to create multiple sessions.
Right. I mean, RPC didn't allow you to do multiple things in parallel on the RPC context, so we kind of wanted to keep that same thing. Now, you could issue multiple things, but from the server standpoint, it didn't actually dispatch them from the RPC layer. It dispatched them serially. It would just buffer them. But we decided to not do the buffering on the server. The client just has to be more well-behaved. Now, there are some perf trade-offs there because the client liked to do what it called pipeline. It would issue a bunch of requests. The server would queue them and it would process them. So you're trying to eliminate some of the transit time with doing that. Now we kind of overcame a little bit of that by allowing the server to actually return larger responses. So instead of just the fixed 96K, we allow it to go to 256K of compressed data. So there's fewer calls to the server to get the same amount of data.
This sequence number, is it across multiple TCP connections? I mean, is it unique or
it's based on the context, or it's based on the session. So it's not unique. It's probably unique, but it's not guaranteed to be unique. Obviously, it's quite small. But it's unique within its session. So it will never reuse the value within that session. And the server keeps track of what the next sequence should be. And if the client doesn't pass it up, then he won't accept the request. And of course, there's the end marker for the chunking. So the session context, the client establishes a session context using the connect for mailbox or bind for address book with the X request type header. The session context is returned as a cookie. The client must treat all cookies as opaque. The client must send all cookies on subsequent requests. And the client must update stored cookies if returned on subsequent requests. So as the client is issuing requests and getting responses, he needs to be updating and keeping track of the cookies if they change. Now, generally, the context, the mapping context won't change, but it could because it's opaque. But the sequence is the one that changes. And also, there's probably some routing cookies that change. So the server destroys the session context with no client activity with a period of time. So the server tells the client how long it will be before it's going to actually expire with the X expiration info. That's the 900,000 value. So a good client, I believe the Outlook client, takes that, halves it, and then issues a request at least once every 7.5 minutes. Now, if the client, there is an actual request type called ping. And essentially, it does nothing. You could pass up the cookies. The request type is ping. And I don't believe it has a request body. And it may have a response body, but I can't remember. It's all in the documentation. And essentially, it just refreshes the context on the server. So it's essentially, you go to the server, and the server says, OK, you have another 15 minutes. And the reason why they have it is because, well, you don't want to do it too narrowly towards the end. And for some reason, half sounds good. I mean, they could do 10 minutes, 2/3, 3/4. So the client should issue a request to the server before the session expires, and the server must restart the session context expiration timer on every client request. So even if it doesn't send a ping, if it's just doing some ROPS or just doing some other operation for NSPI, every time a request comes in, the server has to say, oh, I'm going to refresh the expiration information. So the client gets a whole another 15 minutes. The server also must not start the expiration timer while the request is still processing. So say the request takes 5 minutes to process, and then it sends a done, the 15 minutes starts when it sends the done, not when it initially got the request. So the client should also make the best effort to destroy the session context if it no longer is needed through the disconnect method for mailbox and the unbind for address book. I know the Outlook client isn't real good about this, and I'm having discussions with them where if you just exit the client, they just go away. They don't ever tell the server about it, and of course we eventually run it down. It could present a problem if you started your client, exited your client, started your client, exited your client, started your client, exited your client, because you're going to run out of the number of session contexts you can have on the server. I haven't heard anybody complaining about this, but it's just waiting to happen, I'm sure.
So how many sessions?
I think like 32. I'm not sure exactly, but it depends. The different protocols have different limits. I think it's 32. But the bad thing is the client opens multiple sessions for every instance of the client. So.
Can I ask 2 more questions? Mm-hmm. One, if like, probably it's obvious, but if the connection terminates in the middle of the request, like the server didn't give the response,
yep.
So the client needs to send a request again, or how exactly, what's the status?
Well, if it violates some sort of timing where it sends up the request and it doesn't get the processing or it doesn't get a pending, it just assumes everything's bad. Since it never actually...
assumes the server?
In the response, it actually got the cookie, if it got a response. And the way it is, if you want to try to reconnect, in that scenario it would be a reconnect. If you got a cookie, it's a reconnect. So you essentially just issue the connect again, passing that cookie. So the server says, oh, you're passing me a cookie, but you're also asking me to connect. So the server says, if I have that session, kill it, or run it down, create a new one, and return a new cookie.
Yeah, it's not exactly what I meant. It's like,
sure.
Let's say I ran out of battery. My computer hibernated, right? I was just pending a response from the server. It didn't finish.
Sure.
Okay? I connected power. Now my computer comes out. Outlook has the cookie, right? Won't use it because it hasn't timed out for 3 minutes.
If it doesn't actually finish getting the response, it's gonna fail it. I mean, if you
might get the same request with the same sequence ID, but the server doesn't know that the client has. It will
sure.
Send
if there's a sequence violation, if it sends it up again, if there's a sequence violation, the server just says, "Oh, we're in a bad state. We're in a."
Reconnect.
Yes, it just says, "I'm in a state that I can't recover from. There's a difference between where you're at and where I'm at. Just reconnect."
And then the next question is like, I can do like a connect, then I can do an open on one connection. I can close the connection and then use the handle ID to do a read on the next connection, close the connection and do the second read on the next connection, and just the sequence will grow out between the connections.
Yes, the connection, the TCP connections, that's all independent. As long as you get the response and you're recording the cookies, you can open up another TCP connection and pass it up on a different thing. Yes. Yeah, it's not tied to anything, so you can do that. So we do, on every request, we do validation. If you open up another session and you authenticate, we do the validation that the cookie you're passing up, you are the owner of that cookie. Okay. So there's security. It validates on every request. So even if we didn't say we were just doing HTTP and not HTTPS, and someone could sniff your cookie, they could try to replay it, but unless they authenticate as you, the server will reject it. But you never want someone else to play with your cookies. Okay, so sequencing. The server requires the client wait for the completion of a request before issuing a subsequent request. The server returns a unique sequence cookie on every request and validates the client, sends it to the next request on the next request. So this limits the client from sending multiple requests simultaneously on the same session context. Otherwise, someone could say, well, I want to copy 100 files and I want to do them all at the same time. Would overwhelm the server. So this allows us some ability that we'd be able to detect a bad behaving client before it becomes a problem. But the connect, bind, and notification wait, and I haven't really talked about notification wait, but quickly, I got to hurry up, don't require a sequence cookie. Okay, so it was a protocol transport only change. The MAPIHTTP functionality is equivalent to RPC for EMS, MDB, and NSPI. Previously, when you did EC2 Connect EX, it's essentially the same thing as request type connect. In the RPC world, a context with the server. for a given user, return an RPC context handle, where now we create a session context and we give back a cookie. You could then do subsequent EC2 RPCs for passing up ROPs, and you give the RPC context. Now you can just do the execute request type, which is the same payload, the ROP payload, and you can give the session context cookie. Notifications, it used to be you had to do this weird EC2 async connect to get a new context handle. Then you could do this EC2 async wait. And the reason is that the RPC layer didn't allow two things to be processing at the same time on the same context handle. So the client would create another associated context handle so that one could issue a request and be parked, waiting for notifications while the client could still be doing ROPs. We kind of simplified this with MAPIHTTP. Now it's just notification wait. The client can issue the request. The server will just hang on to the request. We'll immediately respond to it and say pending or processing, and then we'll send the pending every 15 seconds until the server detects, hey, there's something for the client, there's a notification. We complete the notification wait, and then the client, that signals to the client, hey, there's some notifications, and it does the normal execute handshake that it did, like for RPC, to go up and get the ROP notifies. So notifications real quick. Here is a notification wait. Like I explained, you'll initially get the immediate processing from the request. And then every 15 seconds, you'll get a pending. 15 seconds later, you'll get a pending. 15 seconds later, you'll get a pending. 15 seconds later, you'll get a pending. Another pending. 15 seconds later, you'll get a pending, so on and so forth. And eventually, oh, got a new mail. It completes it. And you'll get the response. There's not much response data in the notification wait response, but I think there's like an error code or status code. And it says whether or not there's notification. So, and then, of course, the end marker. So you may see some requests coming through your system where these notification waits are very long, and you'll just see a little bit of data trickling through. And the server will hang on to that call, kind of like in the RPC world, it hung on to the EC2 async wait for 5 minutes. It also hangs on to it for roughly 5 minutes. I think it's anywhere from 5 to 6 minutes, depending on some timer somewhere in there. But it will complete it and say, hey, there's actually no notifications. Just issue another notification wait.
So the pings is for customers, for a client application doesn't want to do wait notification?
Well, the client,
if you do ping,
say a cache client in Outlook, there's one session that's doing kind of the synchronizing. It'll have a notification because it has a table that it's registered for notifications. But it might have another session that's just the background session that submits mail. It has no notification, so it never really needs to get notifications. So on that one, it'll do a ping every 7.5 minutes.
Yeah. So the answer is,
What happened to the notify and also the other ROPs call? There's the notify and the pending calls in the MAPI ROPs.
That's all still there.
Okay.
The whole mechanism of doing like the EC2 RPC, passing no ROPs, and then it gives you the ROP notifies, that's all there. So the notification wait doesn't actually return the notification. It just says, park this call until there's something to tell me about. And when that completes, the client will then do the execute request with no ROPs in the payload, and the server will return the ROP notifies.
Okay, so that doesn't change the behavior.
Right, or if it's doing, say if it's doing some other ROP and it detects there's a notification, it'll return a ROP pending in that response as well. So that mechanism is still all the same.
And you still have to do this one on a separate context.
yeah, because you can't send another request now, right?
Well, notification wait is one of the only ones you don't need to pass the sequence. So the server does not validate the sequence cookie on a notification wait. So you can do a notification wait and you can be doing an execute
Okay. So
in
same
parallel.
things
Yeah.
as it is today.
Yes.
How about asynchronous EMSMDB requests? So what is the...
So the asynchronous EMSMDB used to be where you used to do the EC2 connect. You'd get a context handle for the async interface, and you do the EC2 async wait. Those two things were kind of just merged into one. Now you just do async or notification wait request type. There's no need for the two different interfaces.
So it's just multiplex within the connection.
Yeah.
And you tell them, yeah.
Because we dispatch everything on the server asynchronously anyways at that point. So we could just essentially not complete the call until there's notifications. So performance. So the performance differences are kind of because there's a shift now from very long running HTTP requests where we're just streaming data back and forth. on those streams to now doing many short HTTP requests, so you're doing many HTTP requests versus very few long-running requests. So if there was any like overhead costs in your network based on a per request, whether it's authentication or routing, those are the two main things that we've seen as being kind of performance issues that we're working on and improving them, is being able to route requests through the front ends to the back ends efficiently and also handling the authentication on every request. But mapping over HTTP actually shows fewer overall HTTP requests executing concurrently. Normally when the client's kicked up and it's synced everything and it's just waiting for notification, it really should just have one HTTP request outstanding instead of two for RPC over HTTP. So there's kind of reduction in the number of overall HTTP requests. And the client kind of keeps, the TCP connection with the front end kind of hot or alive because it does have that outstanding notification wait that's parked out there sending the pendings every 15 seconds when there's something from the client. It completes that call, and the client, if it was implemented, would reuse that connection from the connection pool and issue the execute to get the notifications, read down the mail, and then it would then park a call again. So generally you find the client gets kind of sticky with the particular front end, so a lot of the costs for the routing kind of go away because it's a bit sticky. And then also the client can close any unused TCP connections if it has a pool. Let's say it had to open up multiple ones, it could run them down. Whereas in RPC over HTTP, it kept those long-running requests and it had to keep those connections open for long periods of time. So there's also some references. There's the actual documentation. There's probably a repository for it. Whenever I want to find it, I just go to Bing. I type in MS OXCMAPIHTTP, and it always seems to find it. And here's the URL. If you want to scribble it down really quick, is the previous presentation I gave last year for MAPI over HTTP. I think it covered not all of the same things, but some of the same things here. And questions? Yes?
One question about authentication, because we see it's a basic authentication. Do we also have NTLM? But what about?
Well, the authentication is really, it depends. If you're going into, say, like the Office 365 data center, it's basic. I believe there's probably, I think there's work for a different authentication type there. But in an enterprise scenario, it's really, it can do NTLM, negotiate, basic, however you want to configure your front ends. You'll notice that in the auto-discover response that traditionally in RPC, it always returned the authentication type that the client should use to communicate with the server. But in this world, with the HTTP world, we said, well, you know, why do that? Why not just, the client initially doesn't pass any authentication header. And the server says, here are the authentication types I support. And the client picks the one that it feels is the best authentication type for its scenario. And then will authenticate using that type. So once it identifies, hey, this FQDN or this feeder supports that authentication type, it just kind of remembers that and keeps reusing it on subsequent requests for the life of that client session. The next you close the client, you open it again, it's going to re-establish that. It's going to send an anonymous request, and it will, of course, get the 401, and it will, the server will tell the client, hey, I support these. So there's no real configuration that needs to be done in the auto-discovery. You don't have to put some weird stuff in your profile. Because we always had the problem where the server tells the client, here's your authentication type, but then the server changes. And the client's still stuck with an older authentication type and can't connect. So, anything else? Come on.
Well, can you send the presentation to Michael so he can send it to us?
Which one?
This one.
Oh, I think it's probably going to be posted eventually.
You for most of the presentation?
Yeah, all the presentations.
Okay. I think I ran over. Sorry.
Thank you.
Tried to cram a lot in there.